All right, once you're done, I'd like to go to the next question, which is number 2. Look at age ranges. If you have children like I have, you're really familiar with this because when the children are small, you're worried, are they growing fast enough? Are they growing, how fast are they supposed to go? So there's going to be periods in your life you see rapid growth and periods you don't. So look at the age ranges for just the boys' curves and see if you can identify those age ranges where you believe the boys are growing the fastest. And this is going to seem obvious to you when you look at it, but see if you can dissect why you said fastest, what you're looking at. Don't move on. Don't move on. Only stay on number 2. Excuse me, don't move on. Only stay on number 2. No, only go to number 2. And we're trying to work in a group. Are you guys working together?
Yes, I mean, so what is
So we're just looking at these height curves. I know you're writing, but maybe we can start sharing some information together. What do you think? If you're looking at these curves very carefully, what age ranges do you see the fastest growth in boys?
Is it when they're between 2 and 10 because that's when the line is like straight, and after that it curves a little bit.
So what do you think is happening here? We talked about that in one group. Like you see some kind of change here, right? It's that you actually see somebody call it a dent. It's a dent, right? So if you go back down to the age, I cut it off on my page, but you can go and look where that age happens. What age range do you think this dent is occurring at? Somebody other than the front. 10 or 11? What do you think? Puberty. Pre-puberty, right? It seems like, wait a minute, I know that age, right? I have a boy who's 15. I can tell you there's nightmares going on in our house between 10 to 12-ish, 10 to 13. So it looks like it's puberty. Maybe that dent has something to do with puberty. Now we're talking, right? Now we're thinking about something different. What do you see right after puberty? Or it would be right after like this dent. What do you see again? Oh, there's another jump in height. Does anybody have brothers, yourself, guys in class? Have you seen this before?
Yeah. They stay like the same size in one summer.
Yeah, all of a sudden they look like Oliver Twist with their, right, they don't have any, their feet are sticking out of their pants. We usually find this out during orchestra recitals. He doesn't ask us for the suit, and then you see our son is up there with, high water pants. Yeah. And tennis shoes because the shoes that he wore last year didn't fit him. So, of course, he never let us know about this because he also was really moody during that time. So, all of it comes at once. So, and any other change, I asked about the fastest. What about the slowest growth for boys? Where do you start seeing slow growth in height? Right around, like after that, right around here, you start seeing. So, how are we measuring fast growth versus slow growth? What do you mean by fast growth? Slope, right? You're looking at how steep it is, right? When it's really steep, they're growing fast, and when it's not so steep, they're growing slow. How's this different than a line? But if I had a line here instead of these growth charts, you beat lines to death. Right? Every class starts out with and y equals mx plus b. What's slope? It's a straight line. It's a straight line. Is there a portion of the line where they grow faster than slower? No, that's constant growth. Right? They're always growing at the same rate. In medicine, we often use lines. And the argument to stick with lines is that I get this argument a lot. I'm a mathematician that sometimes comes in and says we need to change how we're doing things. In fact, weight changes has been for almost 70 years they've been using a line, and it's still being used. I've written several papers on stopping this, but it's still being used. A line is being used to guide weight loss in people. And why do people use lines? It's easy. And the argument is that's really complex. Can you make it easy? And so I can make you an app. I can program you an app. But I can't make it easy. I can't make the math easy. The math is what it is. You wouldn't want the weather, things that we use to model the weather, they're very complex. They're so complex we can't solve them. And we can only project out a little bit. We know that because we don't look at next month's weather to forecast. We look for today's weather or tomorrow's weather. Somebody said there's going to be a snowstorm on Sunday. So you wouldn't say, hey, Dr. T, there's going to be a snowstorm 1 month from now. What are you going to do about that? Right? Because you expect that to change, right? And that's because those models are very complicated. But it doesn't mean that you wouldn't accept it if someone said, well, I don't want them to be so complicated, so I'll just use a line. So why are we doing it in medicine? Okay, so that's my pitch for why we need to learn complicated math in medicine. The world is changing. The people I work with, they're at the forefront of medicine, they're changing. They're accepting the fact that some of these models have to be more complicated because they're more realistic. And they give answers that are more meaningful. And people want to know, patients want to know what's going to happen to me a year from now. So we want good predictive models that tell us what's going to happen. Okay, I am going to stop there with this. I would like you to hand in, those of you who are not the lead, I would like you to hand in whoever's taking the notes. Or maybe you trust yourself to keep it, you need to keep it until Monday's class so we can continue this. I want to continue this in-class assignment because it's going to give you the why. Now we're going to go into methods, and it's going to be dry as dots. It's just like lab work. Sometimes you're given the instruction for lab work, and you're told, oh, we're going to do this wonderful thing, and then you're in the lab measuring something, and it's boring, right? So there's two sides of math. There's running the suicides, and there's actually the really why. The good stuff is what we saw in grant applications. Here's how we're going to transform medicine, and here's how we're going to do it. That's the good stuff. The dirty stuff, the reviewers never see it. I'm pulled up somewhere in a dusty office trying to figure it out, and that's boring stuff. So we have to do that here too because a lot of it is methods. But I wanted to give you some why because I want to give you some motivation of what we're doing. So this is calculus. If I had explanation of what calculus is, this is it. I'm going to give you the take-home point next time, but the real take-home point is we're looking at curves that don't have constant slope because it's there. You just told me that. There's periods of age ranges where they're growing faster. There's periods where they're growing slower. So someone comes into the doctor's office and says, my 14-year-old's not growing the way they were growing a few years ago. Is something wrong with them? No, their rate of growth is supposed to slow down. This is really normal. Let me show you the growth curve. Maybe you won't show that. My doctor didn't show me that. But maybe you would know that. I know from these growth curves that the rate of growth should slow down around now, so everything's fine. And they might come into your office and say, look, I really wanted my kid to be the center on the basketball team. And they're 18. And they're 5'2". What are you gonna tell them? Get different parents? Get different parents, that's what I was told. Get different parents if you want a dog. I can't. Oh, genetics. We're done. So this gives you information, and the changing rates are important.